All right, let's get going here. Um, so yeah, as I just kind of announced a second ago, the midterm is going to be next start. It goes live next Wednesday morning and will be due by Friday night. So that gives you like 36 hours in there to do it, or I don't know how many hours it is, somewhere in there. 3 days. Yeah, I guess that would be 72 hours. Yeah, 72 hours in there. You can choose to do it, and the way this is going to go down is it's like you have it's open going to be open for 3 days, but you have one chance to do it in one sitting, and it's going to be a 90-minute thing. So I would recommend that you just do it during our normal class time because I know you have that time open. That would be the time to do it. I said it's open for 90 minutes, but it's actually written to be for much less than that. It's supposed to be written for being like about an hour long test. So I mean, give or take, everyone takes their exams a little bit different. So yeah, so that's when it's gonna go. It's gonna go live next Wednesday and be due by Friday night. And so next Tuesday we're gonna do a review, like a review for everything. And also over the weekend, what I'm doing is I'm building study guides, and I'm going to be building a study guides for decibels. Like it's going to have a bunch of examples of how tos, and like I'll give you a lot of different scenarios so that you have something to refer back to, just so that you have an example and with a bunch of examples how to do it. It's not going to be like there's no exam study guide per se. So this is just going to be a subject study guide. It's going to be like an addendum for what we have on decibels, just because I know that there's a lot of number of people out there that it's still not quite sinking in, and that's okay. I get it. Like this is kind of a bizarre. It feels like an out of left field kind of subject. This decibel stuff, but it is one of those things. Once you kind of wrap your head around it and get good at it, it's a good skill to have. So I'll have a study guide for that, and then of course you can use that for the rest of your life if you want. And then I'll also have one on equal loudness contours because I know that that's also kind of confusing for folks as well. And if I can find, like, what I'm looking for right now is like an open source free spectrogram analyzer, because I know that can be kind of confusing for people too. And what really makes the spectrograms um, more useful is if you have the ability to experiment with them and play with them yourself. So I'm trying to come up with one. I can make one if I can't find any, but stay tuned on that one right there. So yeah, so midterm goes reviews next Tuesday, and then the midterm goes live on Wednesday, due morning, and due Friday midnight. So we're not going to have class on next Thursday. So that's because that is midterm time. So it's a little bit. Actually, this is supposed to be midterm. Are you guys doing? Have you guys been doing midterms this week, or are you guys still stuff coming up next week, or when are you guys in the thick of midterms right now? Okay, so they are coming next week. Some people. So okay, yeah. So we're right around the midpoint of the semester right now. I think this is this is class 16. So this is like we have 30 class meetings. So typically. So yeah, we're right kind of in the middle of the semester right now. Sweet. All right. Any questions on that? Any more questions regarding like the logistics stuff? Cool. All right. Let's talk about what we're moving today. So this is gonna we're gonna wrap up the content before the pre midterm content. So this is gonna be on comb filtering, which of course is going to also be on the midterm. So this is up through chapter 10. So if you've been following along, we've pretty much gone through every chapter up through chapter 10 in the book. Some chapters are big, some chapters are thin, and even on the big ones, I'm kind of glossing over some of the other stuff, like the extra points, which I do think are important, but it's just so much content that we can't get through all that in class. So, but I do think it's worthwhile reading it, and I do think it's worthwhile knowing that it's there, because what I found, especially with the book, um, because this book, like I mentioned at the beginning of the semester, this book is what got me into acoustics. And I've put this book to work for me for a number of years, and I think I got like the 3 editions ago was my first one, and I over the course of my career, I find that I refer back to it, and every time I go back through it, I was like, oh, and it connects another dot, and it gets a little bit deeper, and I understand a little bit more. So it's worth keeping this book, and it's worth like reading the information and knowing that it's there, so that when you come across it later in your career, or maybe this spring break. Although during spring break, well, upcoming spring break, you're going to be like, nope, I am checking out. But maybe you want to thumb through things again. If you have some downtime over the summer, just thumb through it again. And what I find is that when you read through the book numerous times, you like learn something every single time. Like it's that kind of a book. So, and it's really useful to our career. So, all right, let's get into it. So we're going to talk about comb filter effects today. We're dedicating an entire lecture on comb filtering, which we've probably all heard about in some regard and experienced it in some a little bit. But let's dig in and really understand comb filtering and its effects, and especially how it affects with acoustics. So comb filter effects. To start with this, so we're gonna take kind of like an on ramp with this sort of thing. So whoops, let me look at my notes here. So when we talk about it, and I think the first thing to talk about with comb filtering is that it works with steady state signals, and they mention this in the book, and that steady state signals are a signal that's constant. Like when I say constant, it's more. It doesn't need to be that it's like a constant sound, but like pink noise or white noise, which does work really well. It could also be something like music. Like when we have music, you can really start to hear it, and we're going to spend some time listening to it today and hear what comb filtering sounds like. But compared to say something like transient, so if you have something like a snare drum, bam, 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 you're not going to really notice the comb filtering as much on something like that. But where you will hear it is on like something like a guitar, or a singing voice, or any kind of like musical, anything that has like a sustain to it. So that's when we're going to really start to notice this comb filtering stuff. But to understand how the stuff works and why it was working, let's start with this concept, what we call superposition. So I'm gonna define it, and then we'll do some demos, and hopefully this will come a little bit clearer. But this idea of what we call superposition. So it says the existence of one wave does not affect the existence of properties of another. In other words, waves pass through one another, and this is true for all waves. So if we think back to what we were talking about with this cocktail party effect just a little bit ago, so like when we talk about that cocktail party effect, right? Where if I'm talking to my friend across from me and I have two people talking across this way, if I'm talking to them, the waves are going all different directions, but the waves are passing over to that person, and the sound waves that are these two people talking are passing across this direction. And it turns out that those waves just pass right through one another without affecting the other one. They do interact and they do pass through each other, but they don't affect the existence or properties of each other wave. So let me do this. Let's do this as an example. Let me pull up an example for this. So let's do. I should have had this, I guess, a link, but already pulled up. So we've used these before, these interactive simulations. So this is from the Physics Up at Sea Boulder. And we want to do, let's clear all these. I think it's just, here we go. Wave on a string is what we want. Let's start this one out. Okay. So what I've got here is, let's do the damping, none. Let's do a pulse. And cool. Let's just let this thing go. Let me pulse this thing. Boom. Okay. So what we're going to do is we're going to use a wave on a string as an analogy for a wave in air. Because like I said also in the slide, that this is true for all waves. This is true for light waves, for sound waves, for water waves, for transverse, for longitudinal waves. Waves pass through one another. Remember, waves are just like they're energy moving through a medium. And the medium stays in the same spot. So we can see here, just to kind of reiterate, that the wave is in motion, but the medium is not. Because you can see like the green dot here, it's going up and down, but it's not going back, and it's not moving along with the wave. So we could say that this is, it's a wave on a string. So this is a transverse wave, because the wave motion is in this direction and back and forth. Wave motion is up and down. So the wave is down, it's moving up, it's moving down. But the wave propagation is moving back and forth. So that's the definition of a transverse wave. So where the wave motion is perpendicular. But we're going to use this as an analogy for the sound wave, because it's just harder to imagine this with sound waves. We'll build up to that model in a minute. But what I'm going to say here is that this wave is now just traveling back and forth and back and forth. Now, what I'm going to do is, let's get this thing across the other side. I'm going to pause it. And what I'm going to do is I'm going to create a second wave when it goes along. All right. So what we can see here is that I have a wave that's on the downside right in here that's about to come back, and a wave on the upside that's traveling towards this little C clamp over here, the clamp that's basically holding it. And what we're saying is that, so basically, and I guess a kind of interesting property here, and this is actually true of sound waves too, is that if we imagine this to be, say, a compression wave for a sound wave, a compression wave, when it hits a wall or a barrier and reflects off of it, it reflects with the opposite phase. So a compression wave comes back as a rarefaction wave. Or in the case of a string, we could say that the top wave reflects back as a bottom wave, which is kind of interesting. So we could say that the phase flips off of a reflection. So when it hits a wall, it reflects at the opposite direction, which is just, well, it's an interesting bit of trivia for right now. Now, what I'm going to do is I'm going to step this thing forward. And what we can see is that I have a wave, again, a positive, I'm just going to define above this displacement line as being positive, and we'll do this one as negative. And when I say positive, negative, I mean negative phase or polarity. So what's going to happen here is that these waves are going to collide. And as they go through it, boom, it looks like they cancel each other out. And for a moment, they do cancel each other out. But really what's happening is they're just passing through one another. The energy is still there. It's just passing through one another. So it keeps on going. So that top wave keeps on going. This is it passing through, and this is the bottom wave, and it's just passing through. So the result is it kind of looks like they're bouncing off each other, but they're not. They're actually just passing through one another. So this is what we call the law of superposition, that waves pass through one another without affecting each other. So it is like, I mean, you could say that if I go through here, that at this point, they seem to be canceling each other out, but that's just because at this point they're passing through one another. They're not actually canceling each other out, because intuition might tell us that something like, if I have a positive, and we're going to talk about this in a minute, if we have a positive and a negative wave, that they cancel each other out. And they do cancel each other out, but only in that one position. Typically, waves are just passing through one another. So when they pass through one another, that's what we call superposition. That's really, I mean, in a nutshell, really what's happening there. Sorry, let me see. Yeah, so we're recording. Lucera, I'm saying yes, this is being recorded. So I recorded and I post all the lectures up, right? Like I try to post them pretty much right after class. So all the lectures are posted on Canvas. And then so phase, well, so in this case we have phase, we say phase is just our perception. No, phase is the polarity. So it's, in other words, in this case, it's a positive or a negative. And we could, in terms of audio, we would call that compression or rarefaction waves. So those are passing through one another. Cool. All right. So let's get back to our description here. Let's pull this back in. So once again, the existence of one wave does not affect the existence or properties of another. So if we think about something like, if I drop a drop of a puddle or whatever in water, if I drop a pebble into a puddle, a pebble into some water, they're going to emanate out, and then those waves are going to pass through one another, and they create some cool patterns, but they just keep on trucking. So actually, this is an example of that right here. So right here, what we did is we all kind of know what these ripples in this water look like right here. So we got some, you can see these concentric circles right here. That means that there is usually a disturbance in the water. So in this case, the water is the medium, and I have a disturbance in there, and those waves are going to propagate out. And it turns out we're actually able to see them pretty well, because this is another cool thing, is this is refraction at work. Remember when we were talking about this idea that bending of waves? Well, when I have a wave, when I take a water wave and I bend it up, what it's going to do is it's going to bend the water. It's going to, well, I can't remember which direction it's going to go, if it's going to bend in or out. But when I have a curved surface of a water, it's going to refract the light to go towards each other and away from each other, and towards each other and away from each other. It's kind of like a lens. And a lens is going to, like, if it's bubbled up, it's going to focus it towards a point. And then if it's up there, if it's in like a valley, it's going to bend it away from it. And so what's going to happen is it gives us the visual cues of refraction. Well, I guess what we can see is that this light is refracted, and we can see the water waves, which is kind of cool without having to look at it from the side. And this is just one of those things that's really pretty. And now when you're at the park next time, or you're like, if you're like in a place where you have in shallow water and you can witness this, just remember that this is refraction at work. We talked about it in terms of acoustics, but this is refraction of light in water. But what we see here is that we've got these concentric circles. And what that means is if we were to kind of extrapolate where the center of the circle is, probably right here. excuse me, that was probably like a pebble thrown in right here or some sort of disturbance. But then we also have one here. We can see that there's another one over here. And maybe there's another one over here. Maybe somebody was just walking by, or maybe they threw a bunch of pebbles in there at once and it just created this kind of ripple effect. But what we can say is that you can see that these concentric circles are passing through one another. And so we see that there's areas that they're like meeting, and there's areas where this is like an intersection right here. And then this is an area where it's like it's an intersection of dark waves, and this is an intersection of light waves, and they're passing through one another. And so even though that they're passing through one another, there's going to be areas where they do either add or subtract from one another. So let's talk about this for a minute. So let's start with this example here. So say I have a wave right here, and we have this properties of waves. Yes. So Peters, yes, you said if two waves in phase pass through one another, that collectively appear to increase in amplitude, and that's exactly what we're doing right now. Yes, or add up. So right here. So if I add two waves right here, and I'm at one position right here, and at my position, these two waves are in phase with one another. The result is we get a larger amplitude. And so what we do is we call that constructive interference. So these waves are interfering with each other at one particular point. So if I'm at a particular point in space, whether it be 2D or 3D space, and at that particular, or I guess it could be 1D if we're looking at the string, but if I was looking at that one particular point, we could say that if they're in phase with one another at a particular point, that they're going to sum, and they're going to constructively interfere with one another, and they're going to actually sum. So in this case, because I'm going to get these two sine waves right here, they're going to get double the amplitude. So that's what we call constructive interference. So constructive interference is when they're in phase and they sum. Destructive interference, so amplitudes double up when in phase. So destructive interference, I guess I don't have a title slide for that, but I should say destructive interference is if I look at this and I add at this one particular position in 2 dimensions or 3 dimensions, if I have these waves passing through me and I happen to have one wave that's actually in phase and one wave that's out of phase, and we sum the two of these together, we can imagine this by adding up the area under the curve. Like this maximum amplitude plus this minimum amplitude equals 0. So in that case, we call that destructive interference. So constructive interference is when they're actually summed together and they increase in amplitude. Destructive interference is when they're out of phase and they reduce in amplitude. Now I'm showing you two of the most extreme cases where they're exactly in phase and where they're exactly out of phase. But the truth is, like a lot of times it's going to be slightly. So like let's take an example. Let's take an example right here. Whoops. My animation's a little screwed up. What if I have two waves that are 90 degrees out of phase? Now this is a little bit of a trippy bit. So if I take two waves that are 90 degrees out of phase, the result is exactly the same wave, but it's just shifted 45 degrees. So, and that's because if I were to add right here, this plus this negative right here is going to be completely negative. And if I were to just sum the two of these together, what it does is actually it phase shifts the wave by 45 degrees, and it's exactly the same amplitude, which is kind of trippy to think about. It's kind of cool. So when we talk about phase, especially in audio, we tend to think about things being in phase or out of phase, like perfectly in phase or 90 or 180 degrees out of phase. But the truth is, like, depending on the delay or the time or where you're at, it could be completely in phase or it could be completely out of phase. So in this case, yeah, so amplitude in this case stays the same with 90 degree phase shift. Pretty interesting. Okay, so let's see. How do I want to do this? So this is when we have like essentially two sound sources. So let's do this. Let's go to that ripple tank that I use, and it's gonna be, let's see, Zoom for whatever reason it's just like this runs stupid fast when I'm not running with Zoom, which is really annoying. Let's do two sources right here. I'm gonna move these apart a little bit. Start this over. Let's lower the frequency a little bit and clear waves. So what I have here is I have two waves that are passing through that are essentially they're outputting the same source at the same amplitude. Let me make it bigger. Uh-oh, did I crash it? There we go. Cool. I'm gonna do it again. Clear waves. Okay, so what I'm going to do is I'm going to define that the bright colors, I'm going to call that an area of compression. And I'm going to define the dark areas as an area of rarefaction. So we have compression and rarefactions. And what this is going to do is these waves that we've been looking at since the beginning of the semester, they're going to be traveling out. And we could imagine this in 3D. They're emanating as a sphere, but we'll just talk about this in 2 dimensions right now, that they're just passing out. And what I've said, the law of superposition states that the presence of 2 waves don't interfere with one another. They pass through one another. So as they go along, and we can think of these like the water waves. So what we can see is that even though this is kind of dim right here, and that this one is kind of dim right here, or let's use the first, like the outside ring, that this is an area of rarefaction and this is an area of rarefaction, that the 2 of these right here, because they're in phase at this point right here, that means they sum together. And you can see that by the way it denotes amplitude is by the intensity of the color in this case. So if it's really dark, that means it's summed together and it's really like low, like the amplitude has increased by a lot, or this rarefaction valley has gotten a lot lower. And the same thing here. If I look at this ring in here, this light colored ring right here, where I'm defining as a compression wave, and then this is a compression wave, that at this point right here, because they're in phase with one another, they're going to be much larger, and it's going to be so along this ring right here, we could say that it's going to be like much larger amplitude along this line right here. So if I were just standing right at this point, I wish I had a marker. I don't know if I can do that. Let's add an object. Let's see if I can do a ellipse, medium speed. Maybe I can just do 1. Let's see if this works. All I'm trying to do is create a visual marker. So like if that was you and you're standing right there, where'd it go? I don't know why I won't stay on screen, but that's okay. Okay. Well, what we can see here is that now we can see that there's areas of you can actually see these like regions of constructive and destructive interference. So in this case, right along this line right here, we can see that's an area of heavily constructive interference. And along this line right here, that's where they're exactly out of phase with one another. So that's a destructive interference line. And actually the term for this is what we're going to call this is an antinode and a node. So I don't know let me see if I have a slide on this. Okay, yeah. I think I threw this slide in out of whack in time. We'll come back to this slide in a minute. I think that one's in the wrong spot. So at 2D and 3D, constructive and destructive. So different frequencies will be constructive and destructive relative to the position of the 2 sources. And the words for this is I'm going to use what's called nodes and antinodes. So in 2D and 3D, constructive and destructive interference lines, they cancel out and add to each other depending on relative position. So nodes are areas and lines of cancellation where it's going to be silent, and antinodes are going to be areas or lines of doubled, summed up amplitudes where it's going to be louder. So what that means is with this one right here is that this is a node. In fact, this is a nodal line along right here, and this is an antinodal line. The effect being that if you were to stand right where my cursor is, it would sound silent. You wouldn't hear it. It's kind of strange to think about this, but this is just this is for frequency of 7. I don't know what 7 means. Maybe it is 7 hertz. But they're just defining this over here as just a frequency of 7. So at frequency 7, if I'm standing right there, it's silent. I can't hear it. It's just not there. And this is trippy to think about, but yes, this is truly the case. And so I'll explain the challenge here in a minute. But if I'm standing over here, so if I'm walking around, I'm going to go quiet, loud, 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 and as I pass through here. So this is the nodal line. So I could say this is a nodal line right here. This is an antinodal line. Node, antinode, node. So a node means cancellation. So a nodal line is like where it cancels itself out. So, but like, so let me try and see. So if I can imagine right here, like extrapolating from this point to this point, the corner right here is an as an antinodal line. So what happens if I change the frequency? So I'm going to change the frequency to 10 now. And so I'm on a node right here's an antinodal line right here. And if I just watch this, let it clear itself out. Huh. Now I'm pretty much on an antinodal line. So what we can say is that these nodes and antinodes are frequency dependent. So it depends on where you are. So at this one, you can see there's a lot more of those nodes and antinodal lines right there. And that's because I increased my frequency. So those nodes became a little bit tighter to one another. And if you want to figure out where those nodes and antinode lines are, I mean, you can actually, it's a pretty neat trick. So what I want you to do, if you're next time you're either in the studio or if you're um listen to I'll get to you in a second. I saw somebody raising their hand. Um, Basically, if you plug one ear and you move your head around and play like play a 1,000 hertz sine wave out of your speakers, out of two speakers, and if you plug one ear and move your head around, you can hear it go wow, wow, wow. It's really fun to do it, and I would normally do this in classroom, but obviously we can't do that right now. And it doesn't work with headphones. You have to be doing out of two sound sources, like actual speakers, for this to work. But the result is that you have areas what we like call hot spots and dead spots. So okay, I had a couple things here. So let's see. Yeah. So the question was okay. So I saw somebody raise their hand. It popped up for a second, but I can't see if you raised your hand. So if you want to just like either hit me up, like just talk in the thing or type it in, that's fine too. Um, but okay. Yep. So the good question, Lucero. I said, how does this affect concerts that use speakers on both sides of the room? It absolutely does. And so this is like back in the, and not even concerts. This is just speakers in general. Anytime you have two sound sources that are playing the same sound, if you move around, you're going to get areas of constructive and destructive interference, and you will get comb filtering. So one of the solutions for this is if you use stuff like hard panning and stereo stuff, that helps mitigate that where you don't have the same sound coming out of both speakers. So right now in this case, what I'm doing is I have both the sound coming out of both speakers. So if I imagine this, like if these are speakers and I'm sitting right here, I'm sitting dead stereo center. The cool thing is if I sit absolutely stereo center, I'm always going to be in an area of constructive interference. So even if I change this to say 21, right here in the middle, well, imagine that this is a control, and if I'm like there, I'm going to be on an area of constructive interference. So if I'm sitting dead center, stereo center between two speakers, this isn't going to be a problem. So, but it's only when you get off axis, then that's when you start moving around here. That's when you're going to start getting this, and you do get this. But part of the way that concerts do this, so to answer your question specifically, if you're at a concert and you're moving around, you will hear this, and it gives it the swishy sound. And you can try it. Part of it is having two ears smears the effect. So having two ears, like basically it blends it, because if this one's in a null and this one's in this is an antinode and this one's in a node, your brain is kind of able to like meld the two of those together. But if you plug one ear, you can definitely hear it as you move around. Also, modern speaker systems like at concerts, they have really sophisticated beamforming. So when you look at those line arrays that are like at big shows, they have very, very sophisticated beamforming. So basically they can aim the frequencies so that they're hitting things, but they're not really interfering much with each other. And especially on the curve going down right here as well. So anytime you have a lot, like a line array is what we call them, like a line array of speakers where you have a lot of speakers going out there, you're going to have this potential. But what they can do is they can actually use this constructive and destructive interference in a way that forms the beam and aims the beam. It's pretty cool. I'm not that familiar with it. I mean, I know of it. I just not that familiar with it right there. So, so this does happen, but that's a great point. That's exactly like what I want you to be thinking about. This kind of stuff does happen all over the place, but we do see that it's frequency dependent. So, what we have here is that we have these areas of nodes and antinodes. And so, like I said, what I want you to do is play next time you have your stereo set up, play a 1 kilohertz tone, plug your one ear. And the reason you're plugging one ear is because, like I said, you're having stereo ears smears the effect. If you plug one ear and move your head around, it's super apparent. You can absolutely hear it get quiet, get loud, get quiet, get loud. So, and it's just like, it's almost like magic. It's crazy. It's pretty cool. So, yeah. Okay. So let's take a look at this. So let's look at this notion of reflected sound. So reflected sound, a second sound source could also be a reflected sound source instead of another source. So specular reflections act as if they were a source on the other side of the wall. So could be a speaker next to a wall or a microphone near a wall. So let's go back and let's do this over here. So we've kind of gotten the idea of what this looks like with these constructive and destructive interference lines. So now what I'm going to do is, let's try this. What is this one? No, that's not what I want. I'll just make it if I can't find one. Let's do a single source. And I'll add a wall. Wall, create it. So now I have a wall. And what I'm going to do is I'm going to move my source next to my wall. Let's clear waves and start us over again. And once again, we see now that what I said there is that basically what a reflection acts like a virtual source. So it's acting like a source that would be exactly over here. So it's like a mirror. Like, you know, that's exactly what it is. It's like a wall is an acoustic mirror. And a mirror, for light, it looks like you have a secondary object on the other side of that. So we have an object that's going to come from over here. And once again, we see that we have this regions of constructive and destructive interference, or nodal and antinodal lines. So an antinodal line right here, a node, antinode, node, antinode, node, antinode. Or we could say destructively interference, constructively interference, destructively interference, constructively, and destructively. Now, what I'm going to do is, if I go to, so I'm using this at whatever generic frequency of 15. If I drop this down to 11, we're going to see that those nodal lines change. The position of these things change. And that's also part of why this does happen in at like concerts and with speakers, but because there's so many different sounds happening at the same time of different nodes and antinodes. So what we're saying here is that I could be at a node for one frequency and an antinode for another frequency, but because there's so many frequencies happening at the same time, the effect kind of gets swamped out. Not to all the way, but it kind of gets swamped out a little bit. So we can see that if I lower the frequency, we get fewer of these right here. But indeed, that we have a nodal line, an antinodal line, a nodal line, or again, constructively interfering with one another. So it's like having two sources that are constructively interfering with one another: destructive, constructive, destructive. So, so what this could be is, this is if you have a speaker next to a wall. So if I have so say I'm at, well, looking down at a room, and I have a speaker next to a wall, and I'm walking around the room. This if the sound is low enough, like if I point the speaker, if the speaker is emanating in a sphere, if I have the speaker pointing in this direction, if I was pointing just straight forward, most of the sound energy is going to go forward, except for low frequencies. Remember, low frequencies diffract. So in the case of a speaker, a low frequency is going to diffract around the speaker, and it's going to emanate as a sphere. So for low frequencies, this is a real problem in a room. For higher frequencies, because high frequencies beam off a speaker, they're not going to wrap around and bounce off the wall, reflect off the wall. Most of the sound energy is going to go straight forward. So we're starting to combine all these kind of subjects here. So we're starting to combine like diffraction with reflection with constructive and destructive interference. So now all these like acoustic kind of properties are starting to glue together. Pretty interesting stuff. Yeah. So it is fascinating. I agree. I think this stuff is really cool. So let's go to really high frequency just to see what happens. Just experiment with this. By the way, if you want to play with this thing, I don't know what I paid for this, this app. It's Mac only. It's on the App Store, but it is really fun to experiment with. There's some really cool stuff you can do with this. I think I can also do this, we do a 3D view. So we can look at this in terms of 3D, but I don't think it's as interesting. I think this one's pretty interesting right here. So at higher frequencies, we can see that it's bouncing off here. We could also say that things like, if this is a sound source and I'm standing over here, so I happen to be at a nodal line right here, but if I change its frequency, then of course it could potentially be, if I'm standing right here, let's see if I happen to hit an antinode or node. Nope, I'm still on an antinode mostly. And that's a region of where they're constructively and destructively interfering. So remember, what I'm saying is that destructive interference and constructive interference are because the waves are passing through one another, but it happens to be at this point where I'm at here, because of superposition, the waves are passing through one another, but at that point, I happen to be in an area where they are summing together, and therefore I get a constructively interference, like a constructive interference on those. Cool. All right. So the other thing, yeah, I guess it could be a speaker next to a wall or a microphone near a wall. So we'll talk about those case studies here in a minute. Now I want to pull this slide in here. What ends up happening is we start to see. So in this case right here, if I have just, and this is just a sound source right here, and this is from the book. I have a sound source right here, and I'm sorry, this is my listener. So my listener is right here, and this is my speaker. So my speaker's playing. Let's just say this is white noise. So the white noise, because this is on a linear scale down here, the white noise playing right here. This is the bandwidth of the white noise. That me listening here. This is the symbol for microphone. If I play along here, I'm just going to get exactly that. So this is what I'm receiving. So this is playing pink or white noise, and this is the spectrum of that white noise. Now, if I get close to a wall, in particular right here. So what I'm going to do is I'm going to get within 0.7 inches of a wall, really close. So this is a microphone right up against the wall. What's going to happen is that this frequency right here is going to be in phase, and then as I go up in frequency, they're going to get out of phase, and in phase, and out of phase, and in phase, and out of phase, and it keeps creating this bump up and up and up and up. And what I'm saying there is that when I've got here, as I go, I wish I had the means to create a transparent object. Let me see. But if I imagine just like something like, we'll just have to imagine it. Let's say this corner right here. That's the best reference that I have. So if I go right here, I'm almost exactly in an antinode. And then if I go up in frequency, let's go 8. Increase the speed a little bit. A lot. So as I go up to 8, it's going to shift slightly more out of phase. And then if I go a little bit more, 9. That as I tend to go, if I hold my position here, as I go up in frequency, it's going to shift, it's going to be between in phase and out of phase, and in phase and out of phase, and in phase and out of phase. So even there, I switch to 9, so I'm getting closer to out of phase. And if I bump up one more to 10 on this corner right here, see if I should be getting close to being out of phase. Oh, probably 9.5 would be out of phase. But we see that it shifted to the other direction, so we can kind of see these lines moving. It's kind of hard to see them, but now as you get to 11, it's probably going to go in phase again, closer to in phase. Yep. So we're getting it right there. And if I go to 12, it's going to go, you can see these shifts. Essentially, they're moving. I guess you could imagine them moving in this direction down here. So you're going 12. 12 is pretty much exactly in phase. 13, it's getting closer to out of phase. So if I was sitting right here, there we go. Yeah, so we're getting closer out of phase. So as I go up in frequency, what we're saying is that I don't know why why is Spotify open? That if I'm standing right here, that as I go up and kill Spotify. That basically, if I fix my position, it's going to go in phase, out of phase, in phase, out of phase, in phase. This is frequency down here. So as I go up in frequency, it's going to go in phase and out of phase. And as I pull further away from the wall, it's going to go in phase, out of phase, in phase, out of phase, in phase, out of phase, in phase, out of phase. So the closer, like basically, it creates this like these areas of constructive interference, destructive interference, constructive, destructive, constructive, destructive. And the result is, and this is where the term comb filtering comes in, right? So this is basically a comb filter. That's what we have, because it looks like a bunch of teeth of a comb. So, and as I go up and as I pull away from the wall, it gets the areas of constructive, destructive interference get closer. So what we can imagine here, what's happened is the sound is coming off of here, and I'm getting the direct sound, and then I'm getting the reflected sound. And depending on the frequency, it's going to be in phase or out of phase. Because essentially, I have an acoustic. If I was to say this is an acoustic mirror, I would have another version of this right over here, and it's essentially like the same sound playing from the other side over here. And then if I move away from this, I'm moving out of this space. That there's going to be regions of constructive and destructive interference. And again, this is the reason we call it a comb filter. In this case, they plotted this out right here as a 0, 5, 10, 15, and 20K. So this is plotted on a logarithmic scale. And so, on a linear scale. My bad. This is on a linear scale. Most of the time when we work in audio, we plot stuff on a logarithmic scale. So we'll take a look at that here in just a second. But we can look at it in terms of a linear scale. Let's see. Cool. Okay, So combining of signals, music, and speech. So let's do this. So rather than use a single frequency, let's use some complex tones. Or I guess this is where that I should have put that slide over here. We'll use white noise since it's easy to see the changes here. So depending on the time delay, some frequencies will be in phase and others will be exactly the opposite. So create frequency regions of constructive and destructive interference. So we could say that the delay can come from either like two sources, like two speakers, or it could come from something like a reflected surface. So I have one sound source and a reflected surface because a reflected surface acts like a virtual second source. Or we can do other things like if I have one sound source, but I have two microphones and that are being summed, that can also cause problems too. So the main thing here is to think of as being time delay. So it looks like a comb. So there is this calculation here. So let's take a look at this. So the null calculations. So the first null, destructive interference value, so is given by the T is the time delay. So F, the frequency, the frequency of the first, I guess just say frequency of the first null is 1 divided by 2 times the time delay. So let's do this as an example. So if there's a 1.5 millisecond time delay between the sources, what are the frequencies of the first three nulls? So let's just talk about this for just a minute before we do the math on this. Just say like, let's get a feel or a concept for what 1.56 talk about what 1.5 milliseconds really means. So if we want to talk about this in terms of the speed of sound, we know that the speed of sound is 344 meters per second because I've made you learn that over and over and over and over again. Does anybody remember what the speed of sound is in feet per second? I don't really talk about it that often, but what is the feet per second of what's the speed of sound in feet per second? Does anybody know that one? Come on. Okay, well, it's 1126, or at least that's the number I always use. Maybe it's 1130. It's around that. We could say we'll just say I'm just going to use 1126 for right now. It's different depending on temperature, but a lot of times you'll see that it's 1,126 feet per second is what we would say. If we want to look at that in terms of milliseconds, we could say that sound travels 1.13 feet in 1 millisecond. So we can roughly estimate. So yeah, okay, so the textbook 1130. We'll use 1130. So 1130 is about the speed of sound. So we can say it's 1.1 feet per second. Or just to keep it simple right now, we can say it's 1 foot per millisecond. So that's how fast travel sounds. In 1 millisecond, sound has traveled a foot. There we go. There's a foot. So that gives us things. So in other words, if I have 1.5, I could say that's about, we could say, again, we're just using just rough approximations here. But if I had two speakers and one speaker's set back by 1.5 feet, that means that's going to be a 1.5 millisecond delay, mostly, crudely speaking. Or if I say that if I have a speaker next to a wall and it has to bounce off the wall and go to me and it has to go, that delay is 1.5 milliseconds. That means it's also had to travel an extra foot and a half. So that's what we can say there. So 1.5 milliseconds is if we're closer to 1.5 feet closer to a source than that. So that 1 millisecond per foot kind of thing is a handy rule of thumb. Okay, so let's do this. So So I'm going to use this thing. So F1 equals 1 over 2t. So F1 equals 1 over 2 times 0.00015, because this is in milliseconds. So t is in seconds, and I gave it to you in milliseconds here. So it's 1,000th of this value. So you have to move it over a couple three decimal spots. So 1.5 milliseconds is the same as 0.0015 seconds. Same difference there. And so I multiply that in, I get 0.003, and that first null is 330 hertz. Rad. That's pretty sweet, I think. So F1 equals 330 hertz. So that means that's for the first null. And then we could say that the F3 is going to be 1,000 hertz because it's 3 times that one. So what I said there is that it's the odd multiples. So when we were looking at this, so even harmonics show up as peaks, the odd harmonics show up as valleys. So so let's use this one as an example. So 1.5 milliseconds. We're going to see a dropout at 330 hertz, at 1,000 hertz, at 1660. And so if I wanted to, I could say that's also going to be at a peak at 666 hertz, at 1,300 hertz, and dot dot dot. You can figure that one out. So we could say here the longer nulls and peaks. The longer the delay, the tighter the closer the peaks and the nulls are. So when they get tight, so as we go up in frequency, they get closer and closer and closer and closer and closer and closer together. And then after a while, they get so tight that we can't discern them. So, and that because it says it's smaller than a critical band of hearing. Our critical band of hearing means what's that's the frequency resolution. It's the tightest frequency resolution that our hearing can hear. We have what we call critical bands. So critical bands are if I have two frequencies that are far apart and I bring them closer and closer and closer and closer together, that after a while they get so close together that our ear sounds to them, it sounds like one tone. I can't hear them as two separate tones. Those are what we call our critical bands. So in concert halls, especially with large room acoustics, it doesn't affect it as much because, well, the high frequency stuff, but also because we have a reverberant space. When I have reflections, a lot of reflections and reverberation, it smears the effect. So we don't really hear it as much. But small rooms like studio and listening rooms, this can be a really big problem. So let's do some demos here. I'm going to use my Max patch here. I whipped up this demo just to do this. And let's do this. Zoom audio. And okay, just get some sound going. Let's turn on my audio. Okay. I don't know why I was. Oh, that was for the demo where we move our heads around, but we don't get to do it with this one. Okay, so I want to do this with some white noise. So let's turn on some white noise here, and it's just cruising along. So we can see that it's like, and we're plotted on a logarithmic scale right now. Is that, yeah? Oh no, that's a linear scale. The linear log. So that's log. Yeah, so that's 8, 16. So yeah, it's 3163. You know, this is log scale right now. Got it. Okay. So I've got this thing with a log scale. So I'm blasting pink noise if we want to hear it. Cool. So now what I'm going to do is I have basically what I'm doing, I mean, it's not that it means anything to you, but really what I'm doing is I have noise going down here and I have it going through I'm playing it twice. So I'm summing the two of these noise signals together. Now what I'm going to do is I'm going to boost this up to 1.5 milliseconds. Okay. I'll turn it down. So let's just look at this for a second and then we'll talk about what's going on there. So what we said there is that with a 1.5 millisecond delay, we did the math that we get a node at 330 hertz. So sure enough, right along here, we see it at 330 hertz. Then we see a peak at 660, and then we see a null at 1,000-ish, and then 1,600, and dot, dot, dot. So if I play this on a linear scale, this is what it looks like. It's kind of smeared out in the high frequencies right here because that's just an artifact of the FFT, but it's actually doing that all the way up through all this stuff here. It's just because the way that this is measuring, it kind of gets swamped out in there, so you can't really see it, but it's actually happening there. So this is on a linear scale. So if we're going through, well, here's 8K to 16K, dot, dot, dot. But here's how we look at it on a logarithmic scale. And so if we want to hear that, so that's without the delay. That's with the delay. Kind of gives it a tubby sound, kind of a weird sound that goes along with it. So what happens if I increase the frequency? So as the frequency increases, the we could call it like the fundamental gets lower. Or sorry, as the time delay increases, the first frequency gets lower, and as a result, these get tighter and tighter and tighter and tighter and tighter up here. Here's a 10 millisecond delay. And at 10 milliseconds, you can really start to hear this. So like, or like Jenna, sorry, I couldn't see it up there. Well, so when you say, where does the two come from? When I say two, that are you saying what two? Which two do you mean? I guess I don't quite understand. Oh, right. Okay. Yeah. So for this equation right here, so um, I don't really. Let me think about that for a second. Why did that come two times the time delay? No, no. Got it. So does this make sense? So it's basically this is just the equation, and I don't actually have to. I haven't really considered how this equation was derived. I just kind of took it for what it is because it just works. So I don't know. I haven't really thought about it, but it's basically yeah. Okay, cool. All right, cool. So in this case, what we have here, and you can hear that definitely like, and beyond 10 milliseconds, you're going to start to hear them as a delay, not as a summed two separate sounds. So, um, like after a certain point, yeah, like it becomes instead of becoming a comb filter, it becomes a delay after you get if you get these two sounds separate far apart in time. But remember, so this 10 milliseconds is like you can imagine it's the equivalent of about 10 feet. Well, actually, it's like 11 feet of sound. So if I have speakers that are 11 feet difference from me, and when I say that they're not, I mean, if you could say that they're in front of one another, 11 feet, but if they're off like this, the distance, the time delay difference is 10 feet between those, that's when I'm going to start getting these comb filtering effects. Or the other time this is going to happen is if I was in a DAW. So we're going to look at a number of different cases here in just a minute on where this thing comes up. But what I want to do is first have you hear this effect. So actually what I should do is I need to grab a tune. Let me put in, sorry, you're going to have to watch me do this real quick, but let's grab I'm going to grab some music just so you can hear what it sounds like. Let's do some music. Let's just grab some. Let's just do something. Just an MJ Thriller. Let's do. Let's do Billie Jean. Cool. So let's send that. Oh, this is going to be kind of a pain. I'm going to send it through here. And I'm just going to do it mono. Here. That should work. I'm going to delete the noise one for a second. Should work. It says white noise, but it's actually music. Wasn't hearing it. Why? Oh, got it. Okay. So let me put this full scale. And then this is the music. So you can definitely see those peaks. Even though we have music trucking along here, you can see those regions of constructive and destructive interference. And let's just hear what that sounds like. So without, raw, with. So what would you say that, like, yeah, so that's what I wanted to say. What does this sound like? Yeah, so flangers are just like oscillating comb filters, exactly. So Dawson said it very succinctly. We can use this as an effect. So we can use these phasers in flangers. So a phaser is exactly that, where they're basically Well, actually, a flanger is, a flanger. The reason they call them flangers is anybody like it's a little bit of trivia, but we call them flangers because what they used to do is when you have tape machines that are playing, the side of a tape machine, those are called flanges, and people used to take their fingers and touch them and let them go, and touch them and let them go. And if you have two reels that are in sync with the same sound, and you slightly delay one and bring it back in phase and out of phase and in phase and out of phase, or well, what I mean is time delay it and then bring it back in. Time delay 0, to say time delay 3 milliseconds, and you slowly bring it time delayed back in and out of oscillate your time delay. It's going to give you that phaser effect, that flanger effect. So it's pretty interesting, and so we can use that for sure as an effect. So, but it kind of gives it that weird tubby sound. Kind of, it sounds strange, right? It sounds just thinner. It sounds tubby. I don't know. There's a lot of different words we can attribute to this thing, but we call it like a tubbier sound or a thinner sound, or it gives it a weird sound. And so sometimes you want to use that as an effect, but generally, it's going to be say it's a bad thing. So it just kind of has that, kind of a strange effect to it. So if you now, well, let's listen to it again, just because I want you to kind of internalize what that sounds like. So let me just play that again. So you can certainly hear it gives it like certain frequencies really get cut out and certain frequencies really get boosted. And it just has that, well, what it sounds like is it sounds like a comb filter. So it just sounds strange. It's like, yeah, it's got like the Tupperware container. So it's basically just kind of got a kind of a strange sound with this. So let's talk about like realistic world. Let's talk about some real world cases where this actually might happen. Let's go back to Keynote for a minute. But the cool thing is you can just do the math yourself and figure it out. So cool. Nulls and peaks. So scenarios where comb filters occurs. So say I have a single mic near a reflective surface, like this case right here. So delay from a reflective surface. So if I have a microphone right here, or like say this is you and this is the sound source right here, the direct sound is gonna come all the way across here, and then the delayed sound is gonna have to bounce down here and come up here. So we could say in this case that I have this is 10.3 feet. So that's going to be a time delay of 10.3 from here to here. But then if I were to measure the length of this one right here, and I can figure out what the length is based off of using some trigonometry right here. But we can see that because it has to travel further, that it has to travel further distance and therefore has a longer delay, that it's going to have, well, because it has to travel farther, the time is going to be a time delay, which we could figure that out. And then therefore it's going to give us a comb filter. So on the flip side, say this guy's actually playing a trumpet right here. And this is a microphone, that the sound is going to come across here and then it's going to reflect off of this. And then I'm also going to get the reflected sound, and that's going to be going to create a comb filter effect. And this absolutely happens. So, if you're looking at your weight, like if you're using a spectrogram and you're basically maybe recording near a hard surface, you will definitely get this sort of sound. Or the same thing happens if I have my speaker, if this is a speaker and this is next to a reflective wall, it's going to bounce off that wall and get to me. And I get this weird reflected, like this weird comb filtering effect. Now, granted, we should say that the reflected sound isn't going to be exactly the same as the direct sound, because the reflected sound is going to get absorbed a little bit. So it's not like truly an acoustic mirror. Something like maybe a super, super hard concrete wall would be something like an acoustic mirror. But if you have something like a gypsum wall and maybe you have some artwork up on the wall, it's going to reflect, but it's not going to be exactly the same waveform. So it's not going to be the comb filter effect isn't going to be quite as strong. But this is why you always want to try to put like reflective surfaces, or absorption around your reflective surfaces that may reflect off of that direct reflection to help mitigate this sort of thing. So but this can be a real problem. So you have to be conscious of this. So if I were to say, maybe I have this trumpet player right here and a microphone right here, I'm doing a distance recording on mic, it may behoove you to actually put acoustic treatment on the floor right there, because that's going to bounce up there and it can cause some problems. And it can, like, depending on how hard the surface is. If it's a really hard tile surface, yeah, you're going to get this, and you're going to get some weird kind of comb filtering off of this thing. But we should also say that if you're playing a trumpet, most of the sound energy off a trumpet is going to be directed forward. Some of it off axis is going to go down and get reflected, but most of the energy for a trumpet is going to go straight off of the trumpet itself. So again, you have to use a little bit of physics, like understanding like directionality and directivity of an instrument. So again, this will define some of your mic placement. So let's look at some other ones right here. So this is multiple mics on multiple sources. So let's think about this in terms of a drum. So drums, if you're recording a drum set, that you're going to have multiple mics set up and you're going to have multiple sound sources. So if I'm hitting a snare drum, it's going to go into the snare mic, but it's also going to go into the tom mic, and it's going to go into the overhead mics, and it's going to go into a lot of the other ones. And that bleed, because it has to travel further, we can figure out what that null is going to be, because from my snare to my tom mic, we'll say it's a rack tom mic, that it's going to be right over here, and then I have my snare mic right here, and I could say that, well, if I measure the distances maybe 5 inches here, and this one's going to be maybe, we'll just keep it simple, 1 foot 5 inches, that it's going to have a 1 millisecond delay between the two of those, that therefore when in my mix, if I sum those two together, they're going to be out of phase with one another. And so this is one of the challenges with drums. When you're recording drums is no small feat. It's just tuning drums takes a long time, and recording drums takes a long time. Drums are just a beast. But this is something that we do have to be concerned about. And so things like, we talk about doing space pair overheads. So if you do a space pair on the overhead, that has potential to be a real problem. So this is why coincident pair makes a lot of sense doing for overheads. If I do a coincident pair, the coincident pair is going to not have any of those potential phase issues for my overhead mics, meaning that no matter if I hit the floor tom or the crash over here or my snare over here, that it's going to hit both those diaphragms at the same time on the microphone. But the cost of doing a coincident pair is that I don't like the stereo width of those things. So for me, when I do drums, I do a spaced pair, because spaced pair gives me a wider sound. But what I do is I tend to do something like, I'll do cardioids face down and get them pretty close to the mic, so that basically this space pair over the snare side is going to pick up this area. This space pair is going to pick up this one. And there is a little bit of bleed, but the signal to noise is so much, we'll say signal to bleed is so much that it kind of negates itself. But I do for the snare is super loud and super transient. So what I do is I match the distance from the snare from this overhead mic to that overhead mic, so that the snare isn't going to be out of phase. We said that it's true that, like, at the first statement I said is that comb filtering is way more apparent on steady state than it is on transient material. So you don't notice it as much on, say, transient, like a snare drum. But you will notice it. It kind of gives it a weird tubby sound. That kind of gives it that kind of strange sound that goes along with it. So yeah. No. So when I say coincident pairs, I mean it's a coincident pair is going to be two separate microphones completely. So two separate XLRs, two separate mics all together. But they just set up an XY or like an ORTF position. So basically I have a cardioid face in this axis and a cardioid, so this is a cardioid mic and this is a cardioid mic. If I put them right here, because they're physically in the same location, if I move them around, this one's going to pick up the left and this one's going to pick up the right. But any sound that hits so a sound coming from the right is going to pick this one up. This one's going to pick up, and the sound coming from the left this one's going to pick up mostly. And anything that's coming from underneath is going to hit both, get equal amplitude in both of them. But because they're in this same physical space location, they are not going to have any time delay difference, and therefore not going to have any comb filtering effects. So the example would be that if I have, let's clear walls. Start this. That if I have this, even if I have multiple sound sources right here, let's go 2 sound sources right here. Even if I have 2 microphones, so maybe this is a snare drum and this is a rack tom, that even if they're 2 together, it wouldn't be that one is, well, actually let's do single source. That if I have a microphone here and a microphone here, that they would not be giving off the same, different time delay. The time delay would be exactly the same for both of those, and therefore they're always going to be in phase. And so that's the benefit of using coincident pairs. And so that is that you're never going to have any phase issues, and those phase issues result as comb filters. When we say that we're using coincident pairs, what we're meaning is that we're using those, and like the reason we use coincident pairs is because there's no phase issues. And when we say that there's phase issues, what we really mean is that there's comb filtering as a result of time delay between diaphragms. And so that's what we're doing there. I know I kind of went off on there. Does that kind of make some sense? Cool. So if we have one source and many mics, so say for instance, so I have a singer, or this shows up as like, you'll see this for like guitar miking techniques. A lot of times when people talk about the rule of thumb that people talk about here is that if you want to so if I've got a guitar cab, so we can imagine a guitar cab as being a sound source, and then I'm gonna hook, this is my guitar cab right here, and I put a microphone right here. Maybe I put a microphone right up on the here. And sometimes people like to pull another microphone a little bit further back to get a little bit of the room reflections so that it gives a little bit of room tone along with it. The problem is that if I have a microphone right here and a microphone right here, is that those are potentially, because they're time delayed, that they're going to have comb filtering. And the rule of thumb, you'll see that people talk about, and maybe talked about one of your classes, is that it's like a 3-to-1 rule. So whatever the distance is for your first mic, is the second mic should be 3 times that distance to try to help reduce this. You're still going to have comb filtering, but in general, that 3-to-1 rule tries to hit it so that it reduces the effects of that. And also, it tends to be that if I get the second mic far enough away, it's going to be what we call decorrelated. It's going to get enough of the secondary reflections in there that it's going to be different than the original wave, and therefore it's not going to have the same. It's not going to have comb filtering issues. When we get into surround sound, that's a big issue, but the term for that, again, is called decorrelated. A correlated sound is when we could say that they're exactly the same, like a waveform is from one source to another source is going to be exactly the same. Decorrelated means that they're going to be different enough from one another that they won't have necessarily many of these comb filtering effects. So we call that correlation. Correlation means how same is how same is the waveform. So what we could also say, things like like basic, well, actually, we'll get to that here in just a second down here, this copy and paste tracks here. So if I have multiple speakers, we kind of went over that quite a bit, but if I have speakers near walls, so this is going to be multiple sound sources. This is going to be reflections, which acts as virtual sound sources. So you're going to have it right here. And then, but here's one that shows up a lot. I see people that, okay, so we're working and we're doing some vocals. We're tracking some vocals and we're like, okay, we want to double up on these vocals. Doubling vocals sounds really good, but the first inclination may be like, well, what if I just copied and pasted it, and then I just slightly delayed the vocals? Well, the result is you get massive comb filtering. This doesn't work because the two signals, like if I copy and paste vocals or any sound source for that matter, but we'll stay with vocals for right now. If I copy and paste vocals and I slightly delay the secondary vocals, they're exactly the same waveform. And what we say that they're exactly correlated. The two waveforms are correlated. Like a correlation value of 1, that they're exactly the same thing. And as a result, because they are exactly the same waveform, you're going to get massive comb filtering. So this is a terrible, terrible idea. I see this happen quite a bit, that people try to do this. That people, on the flip side, on another one, I was working with a client who came in and it was a mixing project. And so they came in and they dropped in all their drum tracks. And I was like, I'm seeing like 3 different copies of kicks in their drum tracks. And I was like, so I asked them, I was like, why do you have 3 kicks in there, like of the same track? And he's like, oh yeah, because it makes it bigger. And I was like, yeah, but they're exactly the same track. It's just, that's the same thing as just turning the gain knob up. It's not like it makes it fatter or doesn't do anything because they're exactly correlated. They're exactly the same waveform. So there's no benefit for doing that. So you could just gain the whole track up or just bring the fader up or clip gain up, and it's exactly the same thing. But yeah, you'll sometimes see like another one is like, if you say you're working with a band that's a 3-piece band, and they want it's like say drum guitar, one, like a single guitar, drum and bass, and that guitarist is playing distorted guitar, and you're like, okay, well, I want to double it up, and so like maybe you copy and paste it to the other track, and then you just delay it a little bit. You're like, nope, that doesn't work, because again, those two waveforms are exactly correlated, so that doesn't work. So what you have to do, so on using something like vocals or guitars or whatever, anything, if you want to double something up, you actually have to double it up. There's doubling algorithms that basically what they try to do is they dynamically delay stuff, and so they give you this kind of pseudo delayed effect that's like doubling effect. But truthfully, is the best way to get a double effect is to double it, like to just play it again. And the reason that works because even if I'm singing, if I'm going ah, and then I record it again ah, that those two waveforms are going to be completely decorrelated. If I go look in and I look at the sample level on those things, those waveforms are going to look completely different than one another. And as a result, that even though they have the same pitch, because they're decorrelated, I will not have any of this comb filtering issues. So that's why you need to, like, if you want to get the doubles, if you want to double stuff up, you have to actually double them up to get that double effect. And I'm a super fan of this. I believe you should, especially on vocals and especially on guitars, you always double everything. Even if you just bring them in a little bit, it gives it a fatness and a thickness without causing any of these time delay, with any of these comb filtering issues. So just know that next time you're like working on a project and you want to make it sound like fatter, like the vocals to just sound plain and too boring, like one of the biggest tricks is to double them up. But what you can't do is you cannot copy and paste them. There are plugins that do these pseudo doubling and they do an okay job, but I don't like it. I don't think it ever works as well as doing the real deal. So what I do is I'll usually, I have a singer sing and then I always have them double it, always. And then depending on the final mix, how much of I want to bring that second one in. And if they're a really, really good singer, they're going to get their articulations almost exactly the same between both tracks, both takes. But sometimes if it's a little bit loose, I'll have to go through and edit that second track in time and articulation and syllables to make it so it matches the first one. And that takes a lot of editing, but that's part of the fun of vocal editing. All right, where are we at in time here? Yeah. Yeah. Yep. So, and the problem is, so if you get comb filtering in the recording process, it's baked in and you're hosed. You can't do anything about it. So, unless like, say for instance, I was doing, say, a guitar and I record it with two different mics, what I can do is I can take that secondary, the mic that's farther away, and if I look at the waveforms, I can shift that back in time. I can nudge that delayed one back in time so that they're in phase with one another, and I can remove that. So I can do that. But if I was doing, say, something with multiple sources and a single mic, or then it's baked into the recording and I can't do anything. So like drums, if I'm getting comb filtering issues and phase issues from drums and I recorded it that way, you're stuck. You can't deal with it. Whereas in the mixing process, I can always undo it. I can change stuff around. So in general, I would say yes, that in both cases, it's a bad idea. It's just, I won't say it's a bad idea. It's physics. It's nature. So you have to be aware of this stuff. And by understanding the effects of time delay, that we can therefore understand how that it's going to affect our phase and our waves, our time delays and our waves, so that therefore we can become better recording and mixing engineers. So, yeah. Cool. All right, my friends. Well, it's 12:15 right now. So I'm going to go ahead and stop the recording and